Hello everyone, and welcome back to the series on intermediate statistics. Today we're going to continue our exploration of non-parametric testing and introduce a little bit more of a powerful version of the sign test for a single median. So let's briefly go over some of the basics that we already know. So last time we began our discussion of non-parametric testing by sort of discussing the pros and cons of doing a non-parametric test, say over a parametric test that say requires your distribution to be normally distributed or your distributions to be homoscedastic to one another. We gave a couple examples of some specific non-parametric tests that we've already done, including a new one, in particular the sign test for the median, that sort of allows us to still conduct null hypotheses and hypothesis tests without assuming anything about the distribution for which we are sampling from. In particular, the sign test for the median is interested in the null hypothesis that the median is equal to some claimed value, say 5, 10, 15, or 20, with the two-tailed alternative typically m is not equal to that particular claim. And how did that particular test, how was it conducted? So first off, we look at our sample S, which usually is a numerical data set that can be ranked from least to greatest. And what we did was we sorted it from least to greatest, placed our claim value on the particular data set, and looked at how many values fell to the left of it and how many values fell to the right of that value. So what we did was, okay, if this is truly the median of our population, then we would like to see approximately 50% of the values to the left of this value and 50% of this value in our sample to the right of it. Right? So that's p hat, and that would be 1 minus p hat, where p hat plus 1 minus p hat would be equal to 1 since it represents percentages. So from this perspective, we're like, okay, well that's just the same thing as saying H0 is equal to P is equal to 50%, and H0P is not equal to 50%. And then from this perspective, then we can say, oh, well that's just a test on a proportion, and then we can do, say, a Wald or a Wilson score or a Grusty-Call test on that particular hypothesis, and then be able to conclude accordingly. Now keep in mind, you can actually slightly manipulate the sign test for the median and actually do any percentile for which you're interested in, because keep in mind a median is just a 50th percentile. So for example, if M0 was the claim value of the 40th percentile, the lower 40th percentile, then we'd like 40% of the data to be less than or equal to it. So the only difference, if you want to change the median to a different percentile, is just compare p hat to a different percentile for which you're interested in, such as 30%, 70%, and 85%. Keep in mind, if you're working on the tails of percentiles, such as near 0 or 1, you should not be using a Wald score, but rather a Wilson score interval, for example, to test that particular value of the proportion. So although that perfectly tests the claims for single medians, a natural question is there a more robust or higher statistical power test compared to the sign test? The answer obviously is going to be yes. And which test is that going to be? That will be the Wilcoxon Signed-Rank Test. So we're not only going to be looking at the signs of the values to the left and to the right of our claim value, we're also going to be looking at the ranks of those values with respect to the median. So let's actually walk through and introduce the Wilcoxon Signed-Rank Test with a nice numerical example. So let's assume our sample set S is going to be equal to 5, 7, 11, 9, 12, 8, just do 14, 10, 11, 9, 13, and 6. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Right? So the size of that is going to be equal to 12. And let's assume we want to test the claim that the median of the population is going to be equal to 10, with the two-tailed alternative that the median of the population is not equal to 10. And let's walk through this Wilcoxon Signed-Rank Test step by step. So what is the very first thing that we need to do? Let's actually organize this via a step process. So step 1. So the first thing that we want to do is calculate S minus the claim value of the median. Right? So when we do that, what will we get? So S minus M0 will be a new set. So what we're going to do is we're going to subtract 10 from every single one of these values. So 5 minus 10, that's going to give us minus 5. 7 minus 10, minus 3. 11 minus 10 is going to be positive 1. 9 minus 10 would be minus 1. And then 2. 8 minus 10 is minus 2. 14 minus 10 would be positive 4. 10 minus 10 will be 0. 11 minus 10 would be 1. 9 minus 10 would be minus 1. 13 minus 10 would be 3. And 6 minus 10 would be minus 4. So this actually starts off the same exact way as the sign test for the median, and pretty much what we do is we count how many positive values we have, how many negative values we have, and both should be approximately equal to 50% each. Right, so that's the step 1 for the Wilcoxon Signed-Rank Test. So step 2 is going to be to calculate the absolute value of S minus M0. So what is that set going to be? So the absolute value of S minus S0 is going to be equal to, so we're just going to take the absolute values of those numbers. So we're going to have 5, 3, 1, 1, 2, 2, 4, 0, 1, 1, 3, and minus 4. Just kidding, that's going to be positive 4. And keep in mind, I am not sorting these from least to greatest. All right, so that's going to be that particular set. And then step 3 is to calculate the ranks of S minus M0, not including zeros, right? So we're going to be ignoring that term there. Okay, so this is where the signed rank, or the rank portion of the signed rank test, actually comes in. So the ranks of these values are going to be as follows. So we're going to have how many values? So we're going to have 5, 3, 1, 1, 2, 2, 4, 1, 1, 3, and 4. Okay. So what are the ranks of these values going to be? So notice that we have 1, 1, 1, 1 there. So 1, 1, and 1, 1. So they all rank or tie ranks for positions 1, 2, 3, and 4. So what we're going to do is we're going to do average tie ranks for these. So the average rank of 1 to 4 is going to be 1 plus 4, which is going to be 5, and 5 divided by 2 is going to be 2.5. So each one of those values is going to get a rank of 2.5. So we're going to have 2.5, 2.5, 2.5, and 2.5. Right, so those are going to be those particular ranks, and now we're going to look at the other values as well. So what is the next value in sequence? So we have 1, 2, 3, 4, and then 5. So the next in sequence would be 2 and 2. So that's going to be 5 and 6, and both of them are tied for rank 5 and 6. So that's going to get a rank of 5.5. So we're going to have 5.5 and 5.5 there. And the next values in sequence are going to be these 3s, and they're tied for ranks 7 and 8, so that's going to get a 7.5. So 7.5 is going to go there, and then 7.5 is going to go there. And then the next in sequence is going to be this 4, and that's going to get rank 9. So that's going to get a rank 9. And then, we also forgot that lonely little 4, so that's tied ranks 9 and 10, so that's going to be 9.5. and 9.5, and then lastly we have rank 11 there, and that appears to be the largest rank that we're going to have in that sequence. So that's going to be rank 11. Okay, notice that we do not have a rank 12 because we eliminated 0. All right, lovely. So that's the ranks of each of these values, and then step 4 is assign the signs of S minus M0 to R. Now, let's go back to our original S minus M0. So notice that we had negative, 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 where are you? There's a negative there, right? So all of those values have a negative sign, so I'm going to put those in front of these ranks as well. So this one's going to be negative, that one's going to be negative, that one's going to be negative. So 1, 2, 3, 4, and then 5 and 6. 1, 2, 3, but keep in mind 0 is not one of them. So it's actually 1, 2, and then negative 1, then 3, and then minus 4. Right? So all those are going to get negative signs, and the rest are going to get positive signs. Right? So these are going to be what we call the sign ranks. So I'm going to call that set SR. So this is going to be equal to minus 11 minus 7.5, and then we're going to have positive 2.5, minus 2.5, positive 5.5, negative 5.5, positive 9.5, positive 2.5, negative 2.5, positive 7.5, and lastly negative 9.5. So once you have those, you can probably sort them, or you could have sorted them earlier on if it makes you feel any better. So let's actually sort this to make it a little bit more cleaner to look at. So we're going to have minus 11, minus 9.5, minus 7.5, minus 5.5, minus 2.5 twice. And then we're going to have our positive 2.5, 1.5, actually no, 2.5 as well. And then we're going to have 5.5, 7.5, and 9.5 accordingly. So notice that we have 1, 2, 3, 4, 5 values to the right, 1, 2, 3, 4, 5, 6 values to the left. Now, in a sign test for the median, it looks about 50-50 split on both of the sides. But the Signed-Rank Test also takes into consideration the ranks, which indirectly considers the distribution or the symmetry or potential symmetry of the distribution for which they are coming from. Right? So it's a little bit more stronger because it takes into account a little bit more. So once we have all of those objects, then step 5 is to calculate these next metrics, which are going to be defined as W plus, which is going to be the sum of the absolute value of the positive ranks, and W minus, which is going to be equal to, not minus 1, just minus. So that's going to be equal to the sum of the absolute value of the negative ranks. I keep on writing minus 1, but it's just minus, right? Once you have that, then the test statistic for the Wilcoxon Signed-Rank Test, which I'm going to call WI stat, will be equal to the minimum of W plus and W minus. There's that minus 1 again. Right? So those are the two primary metrics that we're going to be going for. So we're going to take the absolute value of each of these, and then we're going to add them up. We're going to take the absolute value of each of these and add them up. So once you actually do this, you're actually going to find that W minus will be equal to 38.5 for this example, and W plus will be equal to 27.5. So those are our baby Wilcoxon metrics, and then therefore the Wilcoxon test statistic will be equal to the minimum of these two, 27.5 and 38.5, which is going to be equal to 27.5. So that is going to be our test statistic. So now we need to think about how do we interpret this number. Well, firstly, what is the minimum and the maximum value that this number can even be? Well, the minimum value of the Wilcoxon test statistic is obviously going to be equal to 0. That means you don't have any ranks at all. And then the maximum value of this is going to be equal to the sum of all the ranks, which is just going to be equal to 1 plus 2 plus 3 plus all the way down to n. And that also holds even when you do have tied ranks and you're using the average method. Keep in mind, this is going to be equal to n times n plus 1 over 2 using some identities from pre-calculus that you may remember from before. So for our example, that's going to be equal to 12 times 12 plus 1 divided by 2, which is just going to be equal to 13 times 6, which is just going to be equal to 78. So for this particular example, we have a 78 for the maximum and a 0 for the minimum, right? And if these are pretty much balanced in terms of distribution, then W minus and W plus should be approximately equal to the same exact number, which should be half of 78, which is just going to be equal to 39, right? Somewhere around there. So that's what we're looking for in terms of extremes and ideals, right? So whatever this distribution of this Wilcoxon distribution is, right? So let's assume that this is the Wilcoxon distribution. And let's assume this is going to be for n is equal to 12, because if you change the sample size, these extremes are going to change, right? So the minimum value, that's actually always going to be 0 regardless of the size of n. And for our particular case, this is going to be equal to 78. Right. So here's the Wilcoxon distribution, and half of this distribution is going to be equal to 39. Right? So that's going to be half of 78, which is, keep in mind, n plus 1 divided by 4, where this is n times n plus 1 over 2. Okay? So our particular values are going to be W minus and W plus. So our W minus and W plus came out to what? So we had 27.5, and we also had 38.5. Right? And our test statistic was this lower one. I actually want to leave just a little bit more room in this distribution, because actually I'm sort of stretching out this graph just a little bit, and I don't want to make it misleading. Right? So there's our Wilcoxon test statistic, and if we have evidence to believe that the median is indeed the claim, then both of these should be somewhere near 39. Now, you should note that 27.5 and 38.5 does not equal to our total rank of 78, because we did have some values in our original sample that was equal to the claim. So since that's the case, that's why you see sort of, both of these test statistics sort of lying on the same distribution, which is might be on the surface counterintuitive, but actually not quite. So if 27.5 is actually close to 0, or the higher one, 38.5, is actually close to 78, that's going to give us evidence to believe that the claim value for the median isn't actually the median. Now, if you're looking at both of these values for your test statistics, you're going to have a two-tailed test, but generally speaking, most people will use the left or the minimum value of these two, i.e. the minimum, aka the Wilson or Wilcoxon test statistic. Therefore, the rejection region will entirely be on the left-hand side of this, right? So that's our Wilcoxon test statistic, and we of course need to compare this to our Wilcoxon critical value, which obviously is just going to come from a Wilcoxon distribution for n is equal to 12. Now, you might be thinking, okay, well, what is this actually equal to? Well, I don't know the Wilcoxon distribution. If you actually do, say, a Monte Carlo simulation or something along the lines, you can actually find that this is going to be equal to or approximately 18. Right? So if we just take as an axiom that this is indeed the critical value, we see that our test statistic, 27.5, is greater than the critical value, 18. Therefore, we fail to reject the null hypothesis that the claimed median is equal to 10, right? Which means we have evidence to believe that they are right. Now, if you're not sure how to calculate this thing, no worries. If you're using R, the function is actually pretty nice. So Wilson or Wilcoxon crit is going to be equal to Q SIGNRANK, and since we're entirely in the left, so that's going to be alpha, and then the sample size you're dealing with, so that's going to be 2 in our case, and then lower tail is equal to false. And for this particular example, this is alpha is equal to 0.5. Right? So that's how you can calculate critical values for Wilcoxon distributions in the R world. And that's how you do a Wilcoxon Signed-Rank Test for a single median, which again has more statistical power on average than just a basic sign test for the median. Hope you enjoyed this video, and I'll see you in the next one. Take care.